If I have an infinite sheet of charge of uniform charge distribution, and we'll let the uniform, I'm going to use sigma here. Again, you might look at some other sources that use eta instead. Those seem to be the two big ones. I'm just going to use sigma. And so it's infinitely large. And so from a side point of view, I'm going to be some distance r away. And I'm going to figure out what is the force on the point charge at that distance right there, at that location right there. So this is the side view. This is the jaunty tilt view. So what I'm going to do is, if I have this point here, that's a right angle, I want to look at a a hoop of charge that is the same distance from it. So I have this distance here will be little r, and that will be the radius of the circle. I am going to change one thing. I'm going to make this one L is the distance from there to there, and the radius of the circle is big R. So I have this hoop of charge. So if I have a point right here, then if that is the closest point on my infinite sheet of charge from this point right here, I'm just looking at a hoop where the distance from any point on this hoop to the point in question is the same. So this distance here is the radius of my circle. And so let's come up with some other temporary things right here. This is this angle right here. We're going to make theta. That is a right angle. So I have a couple things to working with right here. So I think I have all the temporary variables that I need. I have my dq right here. I know sigma is equal to dq over dA. Well, my area here, this is similar to what we did before, except it's slightly easier than when we were dealing with the spherically symmetric charge here. Because as I look at this, the distance here from the center of my circle, the center of my hoop to this point is r. So this distance right here, the thickness of my hoop is dr. I don't have to worry about the angle at this point. And so my area of the hoop here, my dA, is going to be equal to 2 pi r, my circumference, times the thickness, dr. And so dq becomes sigma dA from here, which is sigma 2 pi big R dr. So my force at this particular point, again, the force is going to be that way, but I also have a point over here, which is that direction, again, making the symmetry arguments that these will cancel out. Let's set up a coordinate system, so let's just make that the I hat direction. And so the force, keep it in the differential for the start with, is equal to k little q times d big Q over r squared times the cosine of theta, because if that's theta, then that angle there is theta, and I want the horizontal component, horizontal as I've drawn it, in the I hat direction. So F is equal to I hat k q integral d big Q over little r squared cosine theta. This looks very similar to what we've done before, and well, as a matter of fact, it is very similar to what we've done before. We will definitely get a different result though. Q, dq is equal to that. So this is I hat k q sigma 2 pi big R dr over little r squared cosine theta. I have a right triangle right here, so I know that little r squared is equal to big R squared plus L squared, so I can stick that into here. Cosine of theta. Again, I have a right triangle here, so I can use some right triangle trig. Cosine of theta would be equal to L over big R. L over little r. And so this formula becomes, the force is I hat k q sigma 2 pi big R. And we'll do the cosine substitution first, like we did for the infinite line of charge. So I have dr over little r squared Cosine of theta is L over R, which is I hat K Q sigma 2 pi big R. Oh, that is a mistake there. This big R actually should be inside here. It is a variable after all. So this is big R dr over times L over R cubed. Here's my R cubed. L comes out, I hat K Q sigma 2 pi L R dr over R cubed, which is R squared plus L squared to the 3/2. I am assuming that you watched the previously made video, the one with the infinite line of charge first. There are some things that I've done here that I just naturally assume you either can pick up on or you just saw it, or you've seen it at some point. So now I'm left with solving for this. I have a single variable here. L is a constant. That is the distance where little q is from here. And big R is a variable because it depends upon how big this hoop is, because basically I'm going to take this R here from this big R from 0 out to infinity, and those are my limits of integration, so 0 to infinity, since I have a single variable now. And so I have I hat K Q sigma 2 pi L, and then solving this. I'm going to do U substitution here. I'm going to let U is equal to R squared plus L squared. So du is equal to 2R dr. Well, there's R dr right there. And there's my 2. And so this becomes I hat K Q sigma pi L integral from, let's say I have U to the 3/2 on the bottom, and then I have the 2R dr, which is du. I hat K Q sigma pi L integral U to the negative 3/2 du, which is I hat K Q sigma pi L. Add 1, divide by that. So if I add 1, I have U to the negative 1/2 divided by negative 1/2. Now, officially, when you do the U substitution, you change the limits of integration to reflect that. So since R went from 0 to infinity, U would go from L squared to infinity. I tend not to do it that way. I tend to get it down in terms of U here and then substitute R squared back in. That's the physicist engineer in me instead of the mathematician. So UL, and then I get a negative 2 from the dividing by 1/2, or negative 1/2, and then 1 over the square root of R squared plus L squared from 0 to infinity. If I plug infinity in here, I get 1 over some infinitely large number, so that basically gets to be 0. So that's 0 minus, let's do it slightly differently. I get negative I hat 2KQ sigma pi L times 0 minus, I plug a 0 in here, I get 1 over the square root of L squared. The negatives will cancel out. I get an L here. That's going to cancel out. And so I'm left with 2KQ sigma. Notice the distance that this charge is from this infinite sheet is completely irrelevant. It went away. The square root of L squared and that L cancel it out. Oh, and let's not forget the pi. The minus signs cancel out. It is in the direction that is perpendicular to the infinite sheet. Now, putting it in a slightly different form, I know that k is equal to 1 over 4 pi epsilon sub naught. So if I multiply by both sides by 2k, or 2 pi, I get 2 pi k is equal to 1 over 2 epsilon sub naught, and there's my 2 pi k. So I'm left with I hat q sigma over to epsilon sub naught. That becomes an incredibly, there we go. That becomes an incredibly crucial formula for later on when we deal with the parallel plate capacitors and capacitors in general, and actually deriving the displacement current. I cross-reference back to the roadmap that potentially you watched at the very beginning. This is the force on a small charge Q from an infinitely large sheet. And this is one where how close is close enough to assume that it's infinitely large. Generally, we use the 10% rule that if I have a sheet that is L, use different letters, X by X, that as long as the point is within 10% of X, sort of centerish, then we can assume it's infinitely large from its point of view, and that is one of the shortcuts that we will definitely exploit.